So here's an example of what the AIC outputs. So this is, we can keep the model abstract and simply say that this dimension, x dimension, is a function of the model complexity. And then this y dimension is the log likelihood. And so as we increase the model complexity, the log likelihood on the training data is monotonically improving. So we're fitting the data better and better and better. But then if we add the number of parameters that we have to learn as a function of this x-axis, the AIC, as you can see, is still getting better. So the improvement that we get by making a more complex model in terms of the log likelihood is more than enough to compensate for the penalty that we have to pay by introducing new model parameters. So we're still decreasing in this part of the plot. But then at a certain point, the penalty that we're paying by adding more and more parameters is greater than the decrease that we observe in the log likelihood. And so at some point, our AIC penalty is going to increase. And also shown on this plot is the testing performance on a held out test set. And you can see that this also follows the expected pattern, that we improve our testing performance, and then at a certain point we start overfitting our data, and the testing performance, or the testing log likelihood, starts to get worse. And so here, for the same problem, is the 0-1 loss. So this is a classification problem. And so we're plotting here the misclassification error. So we want this to be small. And again, as you can see, so this is the same problem, just showing the plot for a different y-axis. As we increase the complexity of the model, the training performance is getting better and better. So we're classifying our training data better and better and having fewer and fewer errors on our training set as we increase the model complexity. For the testing set, this blue line, we see what we expect to see. As the model gets more complex, we get a better testing performance, but then at a certain point, we start to overfit the training data, and so our testing performance starts to get worse and worse. And the AIC, and so this is an ideal case, this is in this situation, it works out very nicely that the AIC penalty is mimicking that pattern. So the AIC, using the AIC penalty, we would want to pick this model complexity. We would basically use the green line to choose the model, not the orange line. Here's another example of the AIC versus the BIC. So these two combined on an HMM problem. So again, with the HMM, we have to decide how many states are we going to learn in our HMM. And so what this plot here is showing is the negative log likelihood of the data, the sequences that we're modeling, for a 1-state through a 6-state HMM. And so what we can see here is that the negative log likelihood is monotonically decreasing. As we add more and more states to our HMM, we're fitting our training data better and better, and so the negative log likelihood is always going down. The log likelihood is always going up. Also shown here, and this is to compare two different models, is a Gaussian mixture model. So if you remember our discussion about continuous HMMs, they're like Gaussian mixture models, except the Gaussian mixture model generates the cluster assignments IID from a mixing weight on the Gaussians, whereas the HMM has a transition distribution. So if instead of using an HMM to learn the sequences of data, we disregarded the sequential information and just learned a Gaussian mixture model with 2, 3, or 4 Gaussians, we also have our negative log likelihood, which is equal to these 3 numbers. So we see that according to the log likelihood, the HMM is better than the Gaussian mixture model for this data. So we're modeling sequential information with the HMM. However, in both cases, as the model complexity increases, the log likelihood is better, meaning the negative log likelihood is always decreasing. And so we can't use the log likelihood to pick out the model or the model complexity in this case, because we can always pick a number of Gaussians to make the negative log likelihood smaller than HMM for a certain number of states. So we need to use some additional criterion to pick the correct model order And in this case, we could even compare the two models directly. And so here's what's being shown in these two columns, the AIC and the BIC. And so, for example, for the one-state HMM, we have this value, 391, as the negative log likelihood. We then add to that the number of parameters that we have to learn for this particular one-state HMM, and that's equal, and that brings the final penalty to this number. For the BIC, we add the same thing, except we also have 1/2 times the log of the number of observations, and so our BIC penalty is this number. And then as we increase the complexity of the model, we are improving the negative log likelihood by decreasing it, but we're adding more and more of a penalty. And so taking the negative log likelihood for a two-state HMM and adding the penalty for the AIC or the BIC produces this number. And so you can see that by increasing the HMM from one state to two states, we're modeling the data so much better that we still improve the AIC or the BIC. So our improvement in the log likelihood is more than the penalty we're paying for adding more parameters. However, at some point in both of these cases, we start to pay more of a penalty. For example, when we go from a 3 to a 4-state HMM, we're paying more of a penalty for adding those parameters than we're gaining by improving the log likelihood. So here's a plot of that, and we can see that as we add more states, the AIC and the BIC are both improving, but then at some point we start overfitting our data, and both the AIC and BIC start to increase, and because the BIC penalizes model complexity more, the BIC is always greater than the AIC, and also looks like it is potentially picking a less complex model. In the rest of this lecture, I want to discuss the derivation of the BIC in more detail to show where the motivation is for adding this penalty. These numbers aren't simply pulled out of thin air. There's a mathematical reason why we're adding these penalties for these two criteria. They both have their separate motivations. So again, let's recall what is the AIC and what is the BIC for doing model selection. The AIC is going to look at the negative log likelihood and add k, which is the number of parameters in the model. The BIC is going to look at the negative log likelihood and add 1/2 times k times the log of n, where n is the number of observations from the model. So first, let's notice, before we go into more mathematical detail, that algorithmically there's actually no more work that needs to be done. What we do is we simply find the maximum likelihood solution for various model orders. So we run our Gaussian mixture model or HMM, etc., for different model orders, for different model complexities, find the best model in each complexity class, and then find the log likelihood or the negative log likelihood for each of those solutions. And then we simply add to that result either the AIC or the BIC penalty, which we can calculate in advance. These two terms are independent of whatever parameter values the algorithm actually converges to. So the natural question is to ask where these penalties are coming from, because currently they seem a bit arbitrary. So next we're going to discuss the BIC and just simply mention that the AIC has its own theoretical motivations, but we aren't going to discuss those in this course.